second order is a bit slower, and so on. So when you get a bad bracket that is early enough, it's really a strong obstruction to the extent if you have only one control, whatever the order, okay, maybe 10 states, I don't care. If you have only one control, if this bad bracket doesn't vanish, it's a necessary condition for controllability. If this bad bracket doesn't vanish, your system for sure is not controlled. Okay? So this is really a bad bracket. Okay, but here luckily we have two controls, so can we deal with them? I have a bad bracket and another bad bracket. Okay? So system theorem tells you, okay, if you have these bad brackets, you can try to play with them and neutralize them. So indeed, in this example, they can be neutralized. And the system is small time locally controllable because you have accessibility, you have log, I have log here, 1, 2, 3, covering the tension space, and I have bad brackets that can be neutralized. So I'm controllable. But the thing is, what Lewis discovered and made him abandon all this theory, or this approach, I'm sorry, is the following. Let's look at this example and do the following trick. Let's substitute U1, change of variables for U's. I'll change even linear change of variables. So U1 is V1 and V2. U2 is square root V1 minus V2. So I can relate the U's to the V's by this transformation. Okay? So I will replace my problem from the U's like x dot equals f plus g1 u1 plus g2 u2. Okay? So I will replace these u1 and u2 in terms of v1 and v2. So I'll have something like g1 tilde v1 plus g2 tilde v2. Well, obviously this is g1 plus square root g2. This is g1 minus square root g2. Okay? And now I have a new control system in terms of the v's. Obviously, if this guy is controllable, the original guy is controllable, right? Because this controllable means what? For any nearby point, I have a couple of v's that get me there. Well, if you have these couple of v's, here are the corresponding u's that will give you the same thing. So let's look at the Lie bracket structure of this guy instead of the original system. So here we have G1 at the origin. This is 1 square root 2 and 0. G2 at the origin. Actually it's constant, 1 negative square root 2 and 0. Together they cover the two-dimensional space as the original ones. And the Lie bracketing will give you this. G1 tilde, G2 tilde is equal, actually the other way around, at the origin, of course, they are equal 0, 0, negative 8. Neither is a bad bracket, correct? Neither is a bad bracket, because here G1 appears only one time, G2 appears only one time. So I can change the sign of this Lie bracket by changing either the U1 or U2. So just by doing a trivial change of coordinates, linear change, not coordinates even, linear change of controls, and you can do it with change of coordinates too, you can get completely different Lie algebraic structure. So it made him furious upon this approach, and he's now dealing with something called generator free. What do you mean by generator? We mean that these are the generators, like G's and the Lie brackets. So he's trying to make it more abstract and work on a generator-free version. It started in his paper by 2002, and he's doing it on his base so far. We don't have something solid out of this other approach as well, like necessary and sufficient. We don't have up to this point necessary and sufficient. But you can see the point here. Let's do sampling. Do you have any questions so far? So let's do sampling. What's the sample? Linearization is controllable by Kalman. This is a sufficient condition for small-time local controllability. Nonlinear sense. We're talking about nonlinear controllability. Do linearization first, please. This is the easiest thing. If not, then we have the log. the Lie algebraic rank conditions. Go and do Lie brackets. The Lark implies accessibility. Here we're concerned with controllability. If you have Lark and no F, so driftless. No F, because remember, everything comes because of F, right? All the G's, I can reverse their flow. If it's driftless. If you have Lark and driftless, it's STLC. Interestingly, if it's a driftless system, if you do linearization for any driftless system, there is no F. Do Kalman controllability condition. You will get it always not controllable, except when you have n control inputs. I mean, the very luxurious case that will never happen. So your linearization check that we use to do everywhere will never give you controllability in this driftless case. It means that actually we rely on drift to get controllability. And yes, in both cases, in linear and nonlinear, we rely on drift to get controllability. But here the reliance is much more. So this is why, because some people say, yeah, so this covers 90% of the cases, that's fine. But all the driftless systems, which actually the kinematics, if you're dealing with any kinematics, any kinematic problem, pick any mechanical system, get the kinematics. If you treat the positions as your states and velocity as your inputs, so how to go from here to there by manipulating your velocities, and you want to change the position, this by definition will be a driftless system. And linearization will always fail, okay? So Lark plus driftless gives you small time local controllability. Lark plus no bad brackets, which is really too many cases. No bad brackets gives you small time local controllability. Bad brackets, I remind you, are of the type odd and even. Odd for F, even for G, some GG. Lark and bad brackets that can be neutralized by Sussman theorem, 1987. Again, it's small time locally controllable. Lark plus bad brackets that are not neutralizable. What do you get? What do you get here? Any suggestion? Any suggestion? Very good. Yeah, it's only sufficient. And actually, Kautsky, 1990, he provided several examples where you have Lark bad brackets that are not neutralizable, yet they are all small time locally controlled. Okay? Some examples. One last statement here. Lark, we don't require anything. We don't care about the brackets. Okay? So actually, we may be even, you just said that you may have bad brackets that cannot be neutralized, and yet you're small time locally controlled. No, here actually we're saying you may be even not small time local control. That's fine. So you're not small time locally controlled. Okay. But you're satisfying the law, plus your drift is what we call recurrent. What do you mean by recurrent? Well, there is a very formal definition for a recurrent vector field in terms of connections, but we didn't get to connections yet. I'll give you how to view this. Just two examples, the most common examples. F is A times X with A being anti-symmetric. Like 0, 1, negative 1, 0. Something like that, okay? Or more generally, the flow is periodic. Is periodic in T. What do you mean? So, because here's the thing. I'm here. This is my initial point. And here is F. The issue is that I cannot reverse the flow along F, right? So sometimes motion planning requires that I move along F for time epsilon. So flow along, negative F for some time epsilon, right? I need to move here for some time epsilon, but I cannot reverse the flow along F. But if the flow of F itself, its natural dynamics, if you solve the differential equation x dot equals F, and you get the flow is periodic, so it will come here again after a large period t, then this flow is equivalent to the flow along F, right, for t minus epsilon. So I will wait and eventually will come back. If my flow is periodic. So in this case, what do you conclude? If I'm log, so I'm not just living on a slice, I can live everywhere, dimensional wise, but the directionality is not good because of the F, but F itself has this recurrent property, or the flow is periodic. What do you conclude?
Controllability.
Very good, controllability. You can reach eventually, but I'm not small time local control. As you can see here, from one to another, it's weaker and weaker sufficient condition. And when you conclude something where the previous theorems cannot conclude, this is a better result, right? So when I assign homework in this regard, I will just ask, what can you say about the controllability of this system? Controllability properties of this system. You need to get me to the best result ever with these tools, okay? So you need to check everything. Any questions so far?
The last condition is not an existing condition, right?
They are all sufficient.
Sufficient.
They are all sufficient. Any questions? So we'll just keep applying this thing over and over again for a good chunk of the course. And we'll specify for mechanical systems where things are forced by forces, so you directly actuate accelerations, not velocities. So you have cascade of integrators. And then we'll do with time periodic systems, vibrational stabilization. We'll study time periodic system for a little bit, averaging, because Lie brackets can give you some useful tools in averaging. But this is the chunk of our course. So next time we'll do motion planning. I'll assign homework. I'll see if we can assign it today or next time. Any questions? Okay, please feel free to come up with questions. Okay? Your homework is due, right?
Is finished. What is it?